Okay, so let's get started. So, welcome you all to this special seminar on memory-centric computing, enabling fundamentally efficient computers by Professor Onur Mutlu of ETH Zurich. So this is a big bio, so I'm going to take some portions of it.
That gives me more time.
So Professor Mutlu is Professor of Computer Science at ETH Zurich, and he was previously the William and Nancy Strecker Early Career Professor at Carnegie Mellon University. His current research interests are in computer architecture. I don't think most of you know about Onur and his expertise. And he's been working on memory and storage systems. He's very famous for his online lectures that many of us have taken. He's looking at applications as well in the area of bioinformatics. Many techniques that he has pioneered through his group and collaborators over the years have been adopted and employed in commercial microprocessors and memory and storage systems. He obtained his PhD and master's in ECE from UT Austin, and his bachelor's degree in computer engineering and psychology. I didn't know that from University of Michigan Ann Arbor. He has also got some very strong industry experience, having started the computer architecture group at Microsoft Research, and he has held various positions at Intel, AMD, VMware, and Google, and very recently, I think you did a sabbatical at Stanford. Lots of awards. I'll just mention the big ones. Harry Goudet Memorial Award, and from the IEEE Computer Society. He has got the Jean-Claude Lepre Award in Dependable Computing. This is related to the original RowHammer work that Onur did. And 2022 Persistent Impact Prize of the Non-Volatile Memory Systems Workshop, 2021 IEEE HPCA Test of Time Award, and 2020 IEEE Computer Society Edward J. McCluskey Technical Achievement Award. 2019 the ACM Sagar Morris Wells Award, and tons of best paper, top pick paper recognitions at all this top architecture conference. So with that, without further ado, let's give a warm welcome to Professor Onur.
Thank you very much, Suman, for that nice introduction. And thanks everyone for coming. We have some asymmetry here. I'm going to stand here if people are okay, but it's tough to see. It's great to be here. It's always good to be back in Atlanta. I remember Micro was here in 2010 and DSN was here in 2014. But I think this is my first talk at Georgia Tech, if I remember correctly. Okay, so let's get started. As Shimeng mentioned earlier, there are a lot of slides in this talk, but don't be bothered by that. What matters is really what I'm going to say, I think. And we don't need to cover all the slides also. If you have questions, please feel free to ask at any point in time. I'm going to talk about memory-centric computing, but I'm going to give a perspective of some of the research that we're doing in memory systems as well. As Suman mentioned, we do some work on RowHammer memory testing. I'm going to mention some of that too, because I believe it also relates to memory-centric computing. And to solve some of the issues that we have in memory, we need to take a memory-centric approach. Because so far we've been taking a processor-centric approach to actually solve the issues we have with memory, and that's not been working very well for us. And hopefully I'll convince you on what I said. Okay, so today computing is really bottlenecked by data. And data is really key for many workloads. I just put AI, ML, genomics, but there are many, many workloads in the world where we can generate a lot of data. We were talking about physics, for example, astronomy. There's a lot of data generation. All important workloads are data intensive. And we require rapid and efficient processing on large amounts of data. Data is increasing, exploding in some domains. And the analyses that we want to perform on the data is also becoming more sophisticated as we want to do more on the data, as we want the machines to be more and more intelligent, which is a trend. And clearly, machine learning is one domain. I'm not going to harp on this that much. We're going to see some approaches later on. But here, computation requirements as well as memory requirements have been growing exponentially. And people are experimenting with things that are quite interesting, like wafer scale chips, for example. And this is from a talk by Sean Lee, who is the CTO of the Cerebras company, who does wafer scale chips. If you're interested, you can take a look at it. But it's not just machine learning. We do a lot of work in genomics that I'm not going to talk about today, except for flashing some papers maybe. But genomics is an area where actually data is also exploding, because there are a lot of genomes that you can process. There are many biological systems. And one of the data generators in this domain is this nanopore sequencing device. It has sensors, and there's a lot of data that gets generated. There's a lot of analysis that needs to be done, especially if you want to make this a personalized device to give private advice, for example, for you based on everything that happens. And we're doing a lot of work in this area. I'd be happy to talk about that separately. Okay, the problem is we have these data generators that are generating a lot of data, and data access is really a major performance energy bottleneck. Unfortunately, the way we design almost all of our computing systems is based on design principles that don't work well with this data access, meaning we're moving data all around. This is wasting energy because of the fundamental data movement. This is also wasting a lot of performance because fundamentally it requires long latency and a lot of bandwidth if you want to feed a processor. I put this in parentheses over here because we realize this a lot. And we try to overcome this performance loss by making our systems a lot more complicated. We add, for example, many levels of cache hierarchies, many levels of prefetching, many levels of multi-threading, both in software and hardware, out-of-order execution, again, software and hardware. So our systems actually become more complex in hardware and software to tolerate the data movement latency from a data generation device to storage to memory and then to the processor. And that complexity is sometimes warranted when you gain performance, but in many cases, in many applications today, the efficiency at which that complexity works is very low. Meaning you don't gain a lot of performance benefit, but you lose a lot of energy because you added more complexity. So we're in this vicious cycle today. We keep wasting energy because data movement is energy hungry, but we also keep wasting energy because we dedicate most of our systems to overcoming this data movement, and that dedication is not working very well, unfortunately. Okay, that's in parentheses. We're going to get back to that because we add a lot of complexity to our system, and that's kind of hidden cost of data movement, in my opinion. Energy is maybe the not hidden cost, but there's a hidden cost, which is our systems are very complex. And that affects sustainability, etc. So basically, the problem is today's computing systems are processor-centric. All data needs to go through a specific part of a computing unit at great system cost. This is a picture that I drew for my first NSF proposal in 2008. I still like this picture. It's basically a chip, and you can see that there are cores that are the red parts. It could be heterogeneous cores today. But if you look at a chip today, most of it is really dedicated to storing and moving data. Caches, interconnects, other interconnects, memory controllers, memory. And then if you look at a node, even more storage and movement systems. So okay, let's take this picture. If you take this picture, give it to a 10-year-old kid, and ask the question, this is my system. I'm dedicating almost all of my resources, 95% of an entire node, to data storage and movement. This should not be a problem for me, right? Probably any reasonable kid would say, of course not. You're putting a lot of effort into it. But unfortunately, this is our problem still. So our systems are still bottlenecked by memory and storage. When I talk about memory, I talk about storage also. Okay, so let me give you some data on this. This is Google's data from 2015. They have a beautiful paper at ISCA where they showed that more than 50% of the time is spent on, according to them, all of their data center workloads, the processor is waiting for data to come back from memory. It's doing what it's supposed to do only 10 to 20% of the time. What it's supposed to do is finishing instructions, right? Again, it's good to take this blank slate approach and take this kid. You have a 10-year-old kid, ask the question, I designed the system to finish instructions. It's doing what it's supposed to do only 10% of the time. Is this a good system? They'll be honest with you and they'll say, no, it's not a good system. Right? I picked the kid because they don't have this mindset yet, right? Okay, maybe we need to change our mindset a little bit. Okay, so that was performance. Let's talk about energy. Energy is even worse. Again, you could argue with all of these numbers, but these numbers have been shown in many studies. I'll pick Bill Daly's numbers from High Peak 2015 over here. So basically, a complicated arithmetic operation is 20 picojoules. A DRAM access, according to these numbers, is 60 nanojoules. If you optimize things, you can get it down to 1 nanojoule, 2 nanojoules, etc. But the difference is still between 2 to 3 orders of magnitude. And today, we're moving data to do this very simple arithmetic operation. And the reason we actually have a lot of low energy over here is because of technology scaling. Technology scaling has helped us to reduce the energy of logic but it didn't help us with interconnect and the memory cells, etc. Okay, so that was a complicated arithmetic operation. Let's take a look at a simple arithmetic operation, a 32-bit integer compared to a DRAM access, that's 6400x, assuming those numbers again, right? We're not even talking about storage yet. And today, people are trying to reduce the complexity of arithmetic operations, again, for a good reason, to save energy. That saves energy, but still the data moment, it also saves data moment energy, but they say that saves computation energy more than the data moment energy in the end. So as you reduce the complexity of arithmetic operations, the disparity between data moment energy and computation energy will continue to grow. And once you talk about storage, add another 10x over there. So it becomes a little bit almost unreasonable, right, to move the data to the processor. Yet we're doing that. So we also try to quantify the cost of data movement on many applications. This is a study that we did with Google that we published in 2018, where we show that more than 60% of the total system energy on average use cases on mobile workloads like TensorFlow inference, Chrome browsing, etc., is spent on data movement. More recently, we repeated the study on machine learning, edge machine learning models, again used at Google on mobile systems. And in some, especially in large machine learning models, more than 90% of the total system energy is spent on memory. This is just, I'm going to talk about that if you have time to it. I'm going to talk about this work a little bit, but this is our characterization. And if you look at the edge machine learning models used at the time, LSTMs and transducers, most of the energy is really spent on moving data from DRAM and off-chip interconnect to the processor. Okay, basically the fundamental problem we have is processing of data is performed far away from the data. And in the rest of the talk, I would like to motivate a paradigm shift to enable computation with minimal data movement. This doesn't mean that we should compute only where the data source is or where data is stored. We should really enable computation where it makes sense. Today, we have no choice. We basically do computation in a processor. We restrict ourselves. We would like to enable computation everywhere. So this requires making computing architectures more data-centric. And again, this is an example system. If you look at this system, there are many places where computation could be done, but we're restricting ourselves to this, a very small fraction of this SRAM-dominated chiplet to do the computation. Okay, so in the rest of the talk, I'm going to talk about memory as an accelerator also. So how do you actually accelerate computation? But we are designing a lot of accelerators. They're all processor-centric accelerators. They're all bottlenecked by data access. If we actually put computation to the memory side, we will be much less bottlenecked by data. So that's the idea. There's another way of looking at it, actually, not as an accelerator, but all of these are independent agents that communicate together, and everything's a distributed system, and everybody's equal. I think that's also very nice to look at, but that's more futuristic. If you think about accelerator, it's a bit easier to integrate into the current ecosystem, which is really based on accelerators, heterogeneous accelerators. Okay, so this is a very broad slide. Like, what are we trying to accomplish? Essentially, I'm going to talk a lot about main memory. But the idea applies to storage and sensors, etc. Processor, when it gets some sort of computation, it offloads some computation to memory. Ask the question, can you do this computation for me? It could be an instruction, it could be a function, it could be an application, etc. And memory returns the results. Clearly, this looks nice and easy to do, but there are a lot of challenges to enable something like this. How do you design the compute-capable memory and controllers? I'm going to talk a lot about that. How do you design the processor and communication units once you have complete compute-capable memory? How do you design the software and hardware interfaces to enable that? We're doing a lot of work in especially that area, as well as system software compilers and programming models to enable this, because this is really important to do. And also, how do you map your algorithms to the underlying computational memory substrate is important. And finally, this is an area that I am not doing work on, but I hope someone will do work on, which is really theoretical foundations of computing. If you look at the theoretical foundations of computing to characterize the complexity of algorithms, today we count operations. So big O notation, big theta notation, they're all counting operations. But based on everything what we said, maybe it doesn't matter that much. There should be a more data-centric theory of computation that kind of puts things in the right place so that we can optimize the algorithms in a much better way. Again, students who are theoretically inclined, this is a great topic in my opinion. But this is clearly an across-the-stack problem, as you can see over here. Okay, I'm going to talk about processing in memory, but I should also say that this is not a new idea. People have thought about this idea. We're not the first ones to think about it. It's very warm here, so I'm going to take this off. Basically, in 1960s, these are the two major papers that I found from Kautz and Harold Stone that talks about putting logic near memory. This is processing near memory. We're going to talk about the description of it soon. So what has changed today? Why is it interesting? And people have tried this idea many, many times, right? So I think I've motivated the top part. So at the top, applications, our systems are pushing us to be much more memory-centric today. And also today, I think we have some other metrics. We cannot trade off performance and energy with each other because we're very energy limited, and there's also sustainability, and people want to actually optimize all of them at the same time. So maybe minimizing data moment can optimize all of them. But I'm going to switch gears a little bit and talk about the lower level as well. I think at the lower level, we're also being pushed to do something different than being processor-centric. Memory technology scaling is not going well. We're having a lot of issues like retention, RowHammer, etc. And many scaling issues actually demand intelligence in memory, some sort of processing capability. And we've seen this in other technologies like flash, for example. You need processing capability near flash to actually make flash memory work. And I think increasingly with main memory, we're going to see this as well. And also emerging technologies are quite interesting, but I'm not going to talk about that as much. So basically, we're kind of squeezed in the middle today. In my opinion, we have nowhere to escape. And we should really take this approach of data-centric computation. OK, so let me talk about memory technology scaling. We do a lot of work in this area. I'm not going to make this the major focus of talk, but this is, I think, there's a need for memory-centric computing for that person. So we built a lot of infrastructure over many years to understand these technology scaling issues. This is one example infrastructure over here. And we actually expand the infrastructure to many different types of memories. And we're always looking for more memories. This is actually where we did a lot of the RowHammer studies in the RowHammer paper I'm going to talk about. And this was actually the early infrastructure, which is kind of makeshift infrastructure, as you can see. So, and we open sourced this. A lot of people are using it to discover new things as well, which is great. But basically, there are a lot of technology scaling issues that happen when you reduce the size of memory cells. RowHammer is just one example. The reason we built this infrastructure was to study data retention issues. Those are actually very important examples also. So let me quickly talk about the RowHammer issue. Essentially, when you have memory cells that store data, if those cells are big and far away from each other, whenever you access one cell, you're not disturbing the adjacent cells as much. But as you scale the memory technology, when you reduce the size of the cells and put many of them together, there's a lot of noise effects that happen when you access one cell. And in RowHammer, if you keep activating one row repeatedly, that red row over here, the cells that are nearby get disturbed. As a result, they might lose their charge little by little. And if you do the activations enough times within the refresh interval, you corrupt the data, which is clearly not supposed to happen. This is bad for robustness, safety, security, reliability. There's a lot of work on security that builds on this. And as technology scales, this problem becomes much worse. So in 2012, when we originally did our original measurements, there was some number in terms of the number of activations you need to, let's say 100,000 or so. Over the course of 10 years, that number reduced by almost 100x. Basically, to induce a bit flip with RowHammer, it's much easier right now because the cells are smaller and cells are closer to each other. Okay? So we wrote papers, a lot of papers that I'm not going to talk about this. And the problem is getting worse because there are other issues that we keep discovering and figuring out and analyzing. Row press is one example. So it's not just hammering a row, but if you actually activate a row and put the row in the row buffer, the activation actually causes disturbance in adjacent cells. And you actually leak data, leak charge, just because of that activation. So row press effect is keeping the row open for a long time actually disturbs data in adjacent cells. So this makes things a lot worse. Again, I'm not going to go through the details of a lot of these, which is really fascinating. And we have a lot of work. I'd be happy to talk about any of these. So why am I telling you this? Basically, these issues are very, very difficult to solve at the device and circuit levels. You need some architectural system level approach. We always argued this to solve these issues. And you need essentially intelligent controllers that understand that there's something happening in memory, and this should not be happening, and to fix this issue. Now, there's a lot of work. I'm going to mention some of the recent ones later on that develop these intelligent controllers. But the good news is, after 10 years or so, industry is finally picking this up. And this is SK Hynix. They had a paper at ISSCC in 2023 that talks about RowHammer publicly in a published paper the first time. And they describe their solutions to it, which is essentially an intelligent controller in DRAM. So the controller that we envisioned to control DRAM to make it more robust is inside the DRAM chip. They have basically, for each row, they have a counter. And when that counter is greater than some number, they take some action. They don't describe exactly what they do, but this is essentially a controller, which is a step in the right direction, in my opinion. It may not be the best solution, but it's a step in the right direction from a system level perspective. It's a more memory-centric approach to solve the problem, let's say. OK, so this per row activation counting was adopted in JEDEC in 2024, and a lot of companies are building this. The question is, of course, are solutions good? This is one solution to prevent access, as you can see, but kind of easy to bypass, right? So we keep looking at these solutions and providing better solutions. If you're interested, I'm again happy to talk about it. So solutions need to be made more robust, and there are a lot of issues that need to happen. Like, how do you determine the number of activations to decide when to take a preventive action to refresh rows, for example? And there are a lot of issues that goes into it. And we have some papers that talk about that, but I don't have time to discuss this in detail. So I believe there's more to come in this area, actually, because there are a lot of effects that happen when something is in the field. So you have a lot of memories in the field. We're not even talking about space yet. Aging is an issue. So, and we have some preliminary data on aging. We do a lot of work actually understanding aging. But RowHammer becomes worse with aging. Cells become more vulnerable as things become aged. There are papers that we wrote on that topic. And more recently, we've discovered another effect we call variable read disturbance. If you know the retention time, there's variable retention time in memory, which is actually a huge headache in dealing with the retention time. That's the reason ECC is added to memory chips today, so that you don't have very unreasonable refresh periods, etc. But we also found out that the read disturbance threshold of a row changes randomly and unpredictably over time. This is a device level effect that nobody has written papers about. I'm hoping that someone will write device level papers talking about this. That is what happened with RowPress actually. After we published a RowPress paper, some device level folks wrote papers understanding the RowPress effect. So this is actually very fascinating to me because this is a new territory that is being discovered with these infrastructures. And this is the paper that appeared at HPCA if you're interested. We talk about some solutions, but I think solutions in the end, if read disturbance threshold changes, the number of activations you need to make to induce a bit flip changes predictably and randomly, you need a much more conservative solution to solve the problem, and that makes the performance and energy overheads much worse. Okay, so you may actually like emerging memories. I like emerging memories also. I like talking about them. I like working about them, but a lot of them also require intelligent controllers. I'm not going to talk about that. So I think emerging memories will not solve these scaling issues, and whenever they scale to very small technology nodes, they're going to also require intelligence. Okay, so that's why we build this. This is our current infrastructure. This is one of the rooms where we do a lot of memory testing. It's not at capacity yet, but we want to do more of this going forward. The good news is the community is also working on this. There are read disturbance sessions at HPCA, ASPLOS, and upcoming at ISCA. It's great that people are working on it. I should also say that I talked a lot about RowHammer, but it's not just about RowHammer. There are a lot of noise issues like retention time, etc. In fact, that's the main reason why we built this infrastructure, retention time. And it turns out there is a very interesting, let's say, tension between retention and RowHammer. To solve RowHammer, you need to increase refresh rate. And retention is fundamentally, as you reduce the size of the cells, retention becomes worse also. You need to increase the refresh rate. So, but the reason we built this infrastructure was to get rid of refresh as much as possible. But I don't think we're going to get rid of refresh anytime soon easily, let's say. Okay, any questions so far? Because now I'm going to jump to really processing in memory. No questions. I hope I didn't hammer people out. Okay. Okay. Okay, so now I'm going to talk about processing in memory. I view designing memory controllers to manage memory as a sort of computation memory also. Now, if you're doing activation counting in rows, for example, why not use that as storing metadata inside the memory also, right? So there's actually a lot of computation capability that we're building to solve the RowHammer issue. You could actually extend that. But now I'm going to talk about something different. So in my view, there are only two types of processing in memory. One is processing near memory, the other is processing using memory. I'm going to start with the shorter term, easier to adopt version, which is processing near memory, and then I'm going to move to processing using memory, which is the longer term, harder to adopt. In the end, I believe both of these need to be used together. So what's processing near memory? You have logic and you have memory. Normally, these are designed with totally different processes, right? Fabrication, design, testing, everything is different basically in both of them. Processing near memory says put the logic closer and closer and closer and closer to memory structures. It could be inside the DRAM chip. It could be next to each row buffer. It could be next to each cell. But basically, logic and memory are designed completely separately, except logic is closer to memory now. Okay? So that's what we do today, actually, except logic is far away from memory. You could make the logic even farther. That'll be processing farther away from memory. You could make the logic closer. That's processing near memory. So this is easier to adopt, clearly, but there are still challenges because once you cross the boundary of doing computation somewhere else and the processor, you need to deal with adoption issues. Processing using memory is you have logic, you have memory. Forget about logic. You have memory only. This memory has some analog operational characteristics that you can use to actually do computation. And any memory has this computation. I'm going to talk about especially DRAM. And different memories have different types of computation capability also. I think this is fundamentally much more efficient because you're using the memory circuitry and the cells to do the computation. But the types of computation you can do is limited to the characteristics of the memory technology in the end. So in the end, processing near memory is much more capable in terms of what you can do near memory. But processing using memory is much more efficient and much more exploiting the bit level parallelism much better. So in the end, I think we need to combine them. So this is a slide that talks about the differences, but I've already said everything I wanted to say, so I'm going to skip this one. So the good news is processing near memory is already happening today. We have 3D stacked memory technologies that are going to get better and better with packaging, with nicer packaging and integration technologies like hybrid bonding, for example. And over time, monolithic 3D stacking, you have a logic layer under memory layers, and that logic layer can be used to actually do computation near memory layers. And more recently, people have changed their DRAM chips to include processing elements like UpMem. We have a lot of work on UpMem that I'm not going to talk about, but it's very interesting, to have general purpose processing units next to each bank. And also Samsung, SK Hynix, Alibaba, they all built their DRAM chips to have actually near bank computation logic to accelerate machine learning or recommendation system inference applications. These are more specialized. So it's good that there is a lot of action in this space. And with better interfaces like CXL, which enables more computation to be offloaded to somewhere else, people can actually offload computation to different places.
And
yes?
In all these examples,
yes.
The logic die was separately designed and fabbed by a foundry, logic foundry, and then stuff onto the underneath the HBM.
So not all of these are HBM actually. So no, that's not true actually. I think, yeah, I don't. So for example, this one is not a logic die. There's no logic layer here. It's a planar DRAM chip. And you have DRAM macros and logic macros. DRAM macros are designed by company X. Logic macros are designed by company Y. But they're put together by the same, let's say, foundry.
Wow.
Yeah, this is planar. This is not HBM.
But there is no memory foundry. So
well, there's a memory company that does that. Let's say yes.
Yeah. But it's a relaxed, older node that not very advanced node.
Yeah, not very advanced node. That's right. Exactly. That's the key. But here, Samsung has its own manufacturing, right? For example, right? So
Samsung's the only company that has logic,
right.
but they keep it still very separate.
Yeah. And this is GDDR6, for example. There is no logic layer also here. Yeah. So these are different. This is just our example because I'm going to start with that one. But that's a very good question, basically. How do you design these things becomes an issue also going forward, one of the adoption issues. Okay, so let me give you an example. This is a work that we did about 10 years ago. It was rejected multiple times initially, but essentially the idea is you have a logic layer under memory layers, and we believed in the technology. At the time, there was hybrid memory cube, which didn't survive for various reasons. But now we are actually at a point with, for example, hybrid bonding. You can actually have a very nice logic layer and memory layers on top of that. And you can put anything in the logic layer, assuming it's a good logic process. And it has low latency, low energy, high bandwidth connections to the memory layers on top of that. Right? That's the idea. And I think going forward, we'll have even better technologies. And we designed this system. It's essentially an accelerator for graph processing, although it's more general, because in the logic layer, we put an array of cores. Each core is a very simple core because there are thermal and area constraints clearly that you have over here. And these cores communicate with each other with some network. And in the bigger system, you have another array of these 3D cubes. And the idea is to map your graph processing, graph analytics algorithms on top of this hierarchy as well as the hierarchy inside the logic layer. So you partition your graph. When you partition your graph, each core controls, essentially is responsible, owns the memory on top of it. And then when you actually want to perform an operation on a graph node, you send a message to the core that owns the node. Essentially, it's programmed using message passing, remote function calls, which is very similar to how the distributed systems are programmed. You can think of it as a distributed system accelerator for graph processing, essentially. And we do have some prefetching mechanisms to ensure that you exploit the very high bandwidth that's available to the cores. So again, this is a very high-level overview of the idea, and it's a full system-level paper. It's all in simulation because we didn't have the technologies at the time. We compared this Tesseract system to existing technologies at the time. And you see that all of the existing technologies have the processor-memory dichotomy, whereas in this case, processor and memory are coupled, and then you have a distributed system of it. if you think about it, I mean, it's like a machine learning accelerator today, except you don't have processing near memory as we envisioned today. So a lot of the principles are similar to how machine learning accelerators are built today. If you blink, these are GPUs that are connected together with some sort of nice network, right, et cetera. I think GPUs should move to this direction also, but that's a different comment. We didn't look at it. We should have looked at machine learning probably at the time. But you can see that there is a very high memory bandwidth available to many cores. Okay, and the results are quite good. Basically, we saw close to 14x performance improvements average across graph processing algorithms. You need to rewrite your graph processing algorithms to fit this and do nice graph partitioning. Later works improved this to about 100x. And energy improvements is also quite good. And later works also improved it to 100x. We didn't really specialize for graph processing. Later works actually specialized for graph processing and reduced some of the complexities, etc. So I think this is fascinating. In the end, if you have this sort of technology, without changing a whole lot in terms of the technology, you can get a lot of improvement in terms of performance and energy. And you can read the paper. And this was selected to the retrospective in 50 years of ISCA, even though it was rejected multiple times initially. So if your paper is rejected, don't worry. You can still do great work. Just believe in the work. OK, I will skip some of these things. But if you actually take a more system-level approach, if you actually have a set-centric ISA, for example, in structure-set architecture, you can rewrite your graph algorithms much better. And you can also support that much better at the lower levels in processing in memory. And you can get even better results. This paper covers that. And a lot of students did a lot of these graph algorithms. So there are a lot of authors in this paper. Yes, please.
Sorry, in the early example, I think you motivated the work with aggregate bandwidth with all your network cores.
Yeah.
But with the example that you had, I was wondering to what extent are you limited by sort of peer-to-peer connectivity for a general problem? How does one think about capacity versus having to reach out on the network?
That's a great question, basically. And there's no great answer to this because the capacity that you have in this HBM, HMC is going to be limited in the end. And if you have a very large data set, you need to communicate across these. But hopefully that communication is lower than what you would do otherwise. So that's the idea over here. And the graph partitioning affects this a lot. So we actually look at how to partition the graph. People do this in machine learning also, right? They try to optimize for locality as much as possible within a single GPU. So all of those techniques are still applicable to this. But in the end, there is no, let's say, a silver bullet, right? If your data set is too large to accommodate in a single one, you need to distribute. But you do need to use the locality optimizations. OK. OK. Any other questions? Yes, please.
I mean, presumably that it restricts your application space to graph processing. Is that reconfiguration of the communication in hardware, is that something that you would consider as well? Because, or I might be mistaken, is the topology fixed is what I'm asking?
I mean, in our case, topology is fixed, but if you have reconfigurable both computation as well as interconnect, that's great, I think. It basically enables more applications for sure, yes. In our case, actually, we're not restricted to graph processing because we have general purpose in order cores over here. We could have done something else. But our goal was just to showcase this. But if you want to expand the application space, I believe reconfiguration is useful, and also specialized accelerators over here for the applications that you're considering could be very important for machine learning, for example.
There might be a question online.
Oh, OK, online question. Go ahead.
What is the overhead of the PIM in terms of area on the logic-based die, and what is the ratio of the overhead versus HBM I/O infrastructure?
Oh, OK. So that's a good question. We answered that in the paper. I don't have the exact numbers over here, but it depends on the logic process. It depends on the TSVs, et cetera. So if you have hybrid bonding, for example, technology with much, let's say, leaner, thinner interconnect, then you have a lot more area for the logic layer. If you have an infrastructure like HMC where you have TSVs that are huge, then you have a lot less area for the logic layer. So that's why I think integration and packaging technologies are going to be very important to reduce the interconnect overhead that's vertical and enable more area for the logic layer. So technology is on our side, I think, for that question. Yes.
To go back to the previous slide. I mean,
yes.
This is more of a general question. Like
sure.
This figure, I really like when you have this kind of stacks and logic. But You talked about a lot of data, right? So what if that data doesn't fit in that
Yeah.
memory, and now you have many of these?
Yes.
Like, have we just pushed the problem where it's still kind of moving data, it's just less?
Yeah, I think this is very similar to his question, but yes, in the end, you need to partition your graph and exploit locality, yes. But maybe over time you get more layers and you get bigger memories. Applications will also grow, no question about that. That's why I said I think there's no, let's say, silver bullet in this problem. In the end, you need to optimize. If you have too much data, at least in current technologies, there's no good way of really aggregating that data into one place, right? That's why we're looking at in-storage processing, actually. In-storage processing, I think, can solve some of that problem. I will not talk about that in detail. But if you go to storage, then you have a lot of data near flash. And you can actually do that much better. Even then, across the different flash chips, you still need some communication mechanisms, right? So I don't think there's a silver bullet, but in storage, you can do better, frankly. These are great questions. Okay. Okay. So let me quickly talk about machine learning inference so that I have some time for the rest also. But feel free to ask questions still. So this is the work that I mentioned that we did with Google. Essentially, we worked with Google to analyze their proprietary edge machine learning models at the time, and which was executed in edge TPU, which is a smaller version of the Google Cloud TPU, if you're familiar with it. And what we found is there's huge variation in terms of layer characteristics. If you have different layers from different models, for example, if you look at, for example, the arithmetic intensity, there's a huge variation in terms of the arithmetic intensity of the layers, and there's a huge variation in terms of the parameters, input parameters of the layers. And the key takeaway is designing a single accelerator to work on these different characteristics is very difficult. This is also similar to some of the insights that you have, for example, Tushar. The second insight is within each model, even if you look at a single model, there's significant variation across different layers as well in terms of, for example, operations and arithmetic intensity. So today, what people do is they use monolithic accelerators. I think this is also becoming better and better with reconfigurability, etc. But essentially, if you use a monolithic accelerator, it cannot cater for all of these different characteristics. What we designed was a more heterogeneous accelerator. Essentially, you have different accelerators catering to different families of layers. And you have a runtime system that schedules those layers accordingly. We could do better in the runtime system. That's one of the shortcomings. But there's more work to be done in this area. But two of these accelerators are data-centric, meaning you have actually a 3D stacked DRAM and a logic layer. In the logic layer, you have a machine learning accelerator. And these are two different things that cater to two different types of data flows that we found based on the analysis of the workloads. Now, if you actually make these data-centric accelerators, this compute-centric accelerator can be much simpler because it doesn't need to deal with memory-centric layers or data-intensive layers. So in the end, we showed that this, the accelerators in total, their area cost is smaller than the area cost of this accelerator over here. Of course, complexity is higher, right? There's complexity. Okay, so you need to identify the layer families. For that, we use some sort of clustering. You could do this dynamically or statically. There's a lot of interesting work to be done, I think, in this area. And in the end, we show that you get higher performance compared to the baseline HTPU, even if it employs HBM, for example. And you get higher throughput compared to the baseline HTPU as well. Again, this is another example of being memory-centric, where being memory-centric improves both performance and energy. There's no trade-off here, performance and energy. There's more complexity in the system, though. The downside is complexity always. OK, so that's the paper. So we have a lot more results that I'm not going to talk about. Near memory processing is actually very, very interesting. We have done work with Google. Genomics, Genomics is a very nice application in the sense that you can parallelize a lot of it across memory arrays. And we've done some work on this topic. More recently, we moved into storage for exactly the reasons why Tushar and you mentioned. Basically, essentially, if you have very large data sets, it's very hard to fit it in HBM. It's very hard to fit it in even in planar DRAM, even though planar DRAMs are quite good. But flash is huge. And we actually add accelerators, especially in genome analysis, metagenomics, for example. In metagenomics, you have a huge database, like hundreds and hundreds of terabytes of genomes. And you take a sample, let's say, I don't know, from this floor or from this table, and you want to understand what's in the sample, right? So if you want to do that, that's a lot of data that you bring. It's a lot of parallelism also. And in storage, we actually show a lot of good results. Again, I will not talk about this, but I think going forward, one of the important things that we also need to examine in the system is there's also the storage and processing dichotomy, right? Storage, memory, processing. Storage system is a system by itself today. We have memory, we have storage, which is flash, we have memory, which is DRAM, we have some SRAM also, and we have processors over there. You can actually do all kinds of computation over there, ignoring the rest of the system. And we have some inefficiency that's incorporated in the system because you replicate that functionality somewhere else inside the processor as well. Except processors are much better, of course, compute-centric. So I think we need to rethink the entire system to make things better, let's say. OK, so there are many more examples in our paper that we put on archive. We keep updating it for 5 years or so. If you're interested, you can look. And more recently, we've been looking at LLM inference, like a lot of people have. I think there's a lot of benefit from near memory computation, LLM inference as well. I will not talk about these in detail. These are very recent as-post papers. But I think essentially using processing near memory logic and mapping applications, mapping different layers of LLM inference to, for example, different types of processing near memory architectures based on the capacity and bandwidth demands and computation demands of the layers, you can get much better performance. In this case, for example, we have fully connected layers mapped to mapped to near memory processing engines that can do a lot of computation, whereas attention layers, which are very intensive in terms of capacity and that don't require as much computation, mapped to processing near memory engines that are actually less intensive in terms of computation. So I think you can actually diversify the processing near memory space also quite a bit. Any questions? So heterogeneity needs to happen not just in the processing space and also, in my opinion, in the memory space also. And these are some examples of that heterogeneity. I'm going to switch gears to processing using memory now, if we have time. This is going to be more forward-looking. Usually, if we don't have enough time, I ask the question, do people want to cover near memory or using memory? Usually people pick using memory. I didn't give it this choice this time because I want to talk about near memory a little bit also. But let's talk about using memory now. OK, so I'm going to focus on processing using DRAM. As I said, any memory technology has analog operational properties to do computation. Basically, in DRAM, we can do a lot. We can natively support bulk bitwise copy initialization, zeroing. We're going to talk about that first. Bulk bitwise operations, many operations, including functionally complete operations, random number generation, physical unclonable functions, and more complex computation using lookup tables. You can do most of these at low cost, not all of these. You can basically, the idea is to exploit analog computation capability of DRAM. And the lower level idea is you can activate multiple rows, either sequentially or concurrently. If you do that sequentially at quick succession, this performs data copying. If you do that concurrently, this performs computation, bitwise computation. And I'm going to show you results in simulation theory first. And then we have replicated this on our real infrastructure that I showed you earlier. So in real DRAM chips that are not designed for this purpose, you can actually get these functions. That's the really fascinating part to me because clearly DRAM is not designed for this purpose. And the fact that we can actually do some of these operations almost perfectly reliably, copying, in DRAM chips is fascinating. That means that if we actually go and design these chips to do these computations from the get-go, design the sense amplifier, row decoder, word line driver, etc., maybe we can do much more. Right? And this is DRAM. This is not, and with the chips. OK, ignore those numbers, but you get significant performance energy improvements. So let's start by cheating, meaning copy and initialization. This is not computation, but it's still very important. There are a lot of applications that do copy and initialization of data. Google, in their paper that I mentioned, across all of their data center workloads, huge number of workloads, they showed that just these two function calls, memmove and memcopy, consumes 5% of the cycles. That's a huge number for just two function calls. And this is not all the copying that you do in the system, right? You don't have to go through memmove and memcopy to do copying. In their paper, they also say that what I'm going to describe next is a good approach that could be useful. So they reference our paper, which appeared earlier. And I'm going to describe that first. But again, let's take the approach of a 10-year-old kid. Let's say you have this page, 4 kilobytes. Pick your favorite page size, 4 kilobytes. And you want to copy that page to this page over here. If you take this picture and you say, oh, you do computation over here and you have some memory, I want to copy this page to this page and give this to a 10-year-old kid and ask the question, how do you do it? Probably they wouldn't come up with how we do it today. They would probably say, just move it here, right? And we don't do that today, that way. But the idea is to move it that way, essentially. Instead of going through the processor, we do it that way. Again, I'm skipping a lot of things. Today, we have to go through the processor, right? But if you don't have to go through the processor, we could do it inside the memory. And I'm going to show you a mechanism that reduces the latency of a 4 kilobyte page copy from 1,000 nanoseconds to 90 nanoseconds, and the energy from 3.6 microjoule to 0.04 microjoules based on some technology, etc., assumptions. But these don't change that much, actually. Some of the latencies actually increase in some of the newer standards. OK, so let me give you the key idea. This is the fastest you can do that we could figure out. Maybe there's a faster way to do it without a lot of intrusion. The idea is DRAM consists of a lot of subarrays. Inside each DRAM subarray, you have a row buffer. These are sense amplifiers, and you have bit lines and word lines. If you want to copy the source page to a destination page, and they happen to be mapped to the DRAM subarray, hopefully by the operating system before you do the copy, you first activate the source row, which brings the data into the row buffer. Now the data is strong in the sense amplifiers. Now, the next thing you do is, in quick succession, activate row B, which implicitly deactivates row A, and connects the sense amplifiers to the cells in the row B. Because sense amplifiers are strong, now the data is copied into row B. By doing 2 consecutive activates, you can actually do this copy very fast. And it's negligible hardware cost. In fact, you can do this in DRAM chips by violating the 2 back-to-back activate parameters. I'm going to show that later on. OK, so if you do this, you get significant latency and energy improvements. Clearly, this works when data is mapped to the same subarray. What if they're in different banks? And we have mechanisms for that also in the paper. We have actually other mechanisms to improve that later on that I'm not going to talk about. Yes?
Sorry, how did you bypass the precharge on commodity data?
How do you bypass the precharge? You just do 2 consecutive activates. Oh, how do you bypass? Because in commodity DRAM, chips do not require a precharge. They don't check. So you do activate, you send another activate, you can do it. If they disallow it, yeah, you wouldn't be able to do that. And unfortunately, some manufacturers disallow it sometimes. And then you cannot test their chips, which is a loss in terms of like science, let's say. Right? But yes, that's a very good question in that sense.
What about night? Yeah. So normally the action would have been you read A comes to row buffer, read B comes to row buffer.
That's right.
Row buffer. Here, like it kind of did the opposite, right? Row buffer moved it.
That's right.
Is there a security vulnerability now? You could rewrite stuff because of this?
So that's a great question. We have a paper coming up at DSN that talks about the security vulnerabilities. So the security vulnerability really is a side channel, right? Because you're doing it close to memory, inside the memory, the bandwidth of the side channel is much larger than the bandwidth of the side channel you can get inside the processor. Because inside the processor, if you want to measure the timing, you have to go through the hierarchy, and it's a very low bandwidth side channel. But we show in our upcoming DSM paper that there's a much higher bandwidth side channel. We don't know of any other, or a quart channel, essentially. Yeah. Is that what you were thinking of?
Yeah, I was thinking about this, again, related to your RowHammer attack, right? Like you had some other page where you just replaced the data in that page.
I see. So, OK, that's another paper. So basically, how does this affect RowHammer? I think that's also a great question, and we investigated that question. We have a paper coming up at ISCA that talks about it. And this makes RowHammer much worse, no question about that. But it makes RowHammer much worse if you do it many, many times. If you do it one time, it's OK. If you have some RowHammer solution internally, it'll be OK, but maybe the overheads are large. But yes, clearly this is going to not help RowHammer because you're doing it much faster over here. These are very good questions. That's part of the adoption issues that I'm going to talk about later on. Like there are security adoption issues that will come up also, and robustness adoption issues. OK, so that was RowClone. We show some results that are good at the application level. Let's talk about computation. Essentially, if you want to do computation, you need to activate multiple rows concurrently, at least the way we do it. So imagine these 3 cells. These 3 cells are capacitors in DRAM. They have some access transistors that are not connected. They connect to the same bit line. If you concurrently activate these 3 cells, you will perform computation. And this is just 3 cells, but there are actually 4 kilobytes or 8 kilobytes of these cells. And imagine doing this operation on millions of cells concurrently in DRAM. Now, if you concurrently activate these 3 cells, they all get connected based on charge sharing principles, similar to RowClone. If at least 2 of these cells are charged, you get the charge state at the end, at the top end of the sense amplifier. If at least 2 of these cells are discharged, you get the discharge state at the end. So this is a bitwise majority function, basically. So now you can do bitwise majority, again, based on circuit theory, ignoring all the variation. With some variation, of course, there's some potential for errors, etc. But you get the majority function. And majority function is nice. Knuth actually makes a big deal of majority function, which is beautiful, I think. If you haven't read Knuth's Art of Computer Programming, he talks about then, I think, volume 4. Essentially, if you set C to 1, you get the OR function. If you set C to 0, you get the AND function. Clearly, this is not functionally complete. You cannot map everything to it. But functional completeness is also possible. You just need an inversion, right? If you activate one row, you sense the row data over here, and the complement is actually over here. So you actually have the NOT function already in DRAM. The problem is it's somewhere else. So in this work, we suggested that you actually put it back here, which actually adds cost to DRAM. But if you want to have the NOT function in the same subarray after you activate one row, you need to put it back here somewhere in some way. Again, I will not go into the details of it. This is a bit harder than majority function, but it's possible to do if you want to pay some cost. Now, if you have a functionally complete substrate, majority plus NOT, you can map any application to it. In this work, we actually looked at a lot of different things, including databases, and you get significant performance and energy improvements. Okay. And there are a lot of other applications that you can actually map that we did not explore. A lot of applications actually do bitwise operations. If you actually re-express your applications to do a lot of bitwise computation, like set operations, that's one of the reasons why we actually rewrote a lot of the graph algorithms to be set-based, because this is great for set operations like set union, set intersection, etc. And you get a lot more applications covered by this sort of substrate. Okay, there's more on Mbit. If you're interested, you can take a look at it. So how do you make this more programmable? More recently, we've been looking at how to make things more programmable in both processing using memory as well as processing near memory. I'm going to give you one framework that's applicable to both, but it essentially abstracts things such that we preserve the existing programming model. So if you want to implement some operation, it could be a matrix multiplication, for example. It could be a convolution. It could be just division, whatever you want. You express it in terms of how we describe hardware and or not logic. And then we use some design automation tools that are developed for actually superconducting logic by EPFL to optimize that majority inverter graph. And we actually turn that into a microprogram that is a sequence of DRAM commands to perform this circuit, essentially. And we store that microprogram as a new instruction. Essentially, we associate that microprogram with an instruction. It could be convolution again. And then the compiler or the programmer inserts this instruction in their program. And this instruction gets shipped to the memory controller, and that microprogram gets executed. So that's a very general way of incorporating processing using memory, as well as processing near memory operations. But in this case, we showcase processing using memory. And we see that you get significant performance and energy improvements with this optimization. Yes?
I have a question online. It says, after bitwise operations, how do you write back to original state that the data is going to be reused later?
Oh, okay. You need to copy first. Yes. So if you concurrently activate 3 rows, you write the result to all of those 3 rows in the end. So you lose the original data. If you want to actually keep the original data, you need to copy it first. Actually, our paper is a little bit more nuanced than that. There are other issues, meaning if you want to concurrently activate any arbitrary row in a subarray, your row decoder becomes terrible. It's very complicated. So you actually need 3 row decoders, essentially. And we don't want to do that in DRAM. We actually have a separate part of the subarray reserved for triple row activation. You copy the data to that separate part of the subarray first, and then you do a triple row activation with very little decoding logic. And that actually solves that problem as well. So that's a very good question, but there are a lot of other implementation issues as well. Any other questions?
So
yes.
Functionally, could you do the same thing with SRAM as well? I'm curious.
Yes, exactly. So there are papers that talk about that. Compute caches, for example. Yes, retools work, for example, yeah. Yeah, functionally, I think, actually, I'm not going to talk about that, but we showed that you could do it in Flash also. Not exactly the same thing, but concurrent row activation, multiple row activation is a primitive that could be used for many memories. And people have shown in simulation you could do this for NVM, PCM, etc. So it's definitely a primitive that could be used for many memories, although the functions you get may be a little bit different depending on the type of the memory. Yeah. I think, I mean, we can talk about SRAM versus DRAM, but SRAM is very small in my opinion, so it's very hard to get some big thing done with SRAM. If you're complaining about the size of the DRAM over there, SRAM, you should complain even more. But it's good to investigate, no question about that, right? There are conditions under which some of these memories are actually quite useful. Right?
So is DRAM the sweet spot in terms of ROI, or as the ROI increases as you go to the NAND?
Oh, okay, that's a great question. I think certainly depend on the data set size. Depends on how much data movement you have, right? I think in the end we need to enable computation capability everywhere, including SRAM. Don't get me wrong, based on that comment. And we need, in my opinion, we need a system that ships the computation to the right place. Okay. That's kind of a longer term vision. We're not there yet, clearly, but we're trying to also figure out where should the computation be done with some runtime system design. Okay. Okay, let me talk about this work quickly, and then I'll talk about real chip results, and then hopefully we'll take more questions. Basically, we wanted to target other issues with this processing using this DRAM system. One of the issues is, if I'm running late, please let me know. Yeah. One of the issues is whenever you do an operation, it happens on 8 kilobytes of data, or whatever your row size is. And this is huge, actually. The reason is not a lot of the operations are that parallel, especially in general purpose applications. So we wanted to get rid of that inefficiency. You want to do, let's say, 512-bit operation, which is really the vector length of many processors today, which compilers target. You really want to do that operation on 512 bits and not 8,000 bits, because the rest of it will be wasted. So the idea over here is we want to use fine-grained DRAM. We want to modify DRAM slightly such that we can activate every individual mat. And this is not a new idea. People have designed fine-grained DRAM ideas. We just use it, and we also have a design also. But basically, the idea is you can activate each mat separately. And now you can actually pack different operations such that they happen in different mats. It could be a VLIW operation. It could be different operations that happen at different times. Essentially, we have a multiple instruction, multiple data execution model such that different mats can execute different operations. That's the idea over here. And we have a sector DRAM design which enables this. If people are interested, I'd be happy to talk about it, but we don't have time. And then clearly, some operations like reduction operations, aggregation operations need some logic. And you cannot do that. You don't want to do that by going to the logic layer or somewhere else. So we add some interconnects for vector reduction in this particular case. And maybe even more importantly, the fact that we can restrict the operations to happen only to 512 columns enables us to target existing compilers like LLVM to actually do these, to actually extract parallelism and also map it to the DRAM mats. So in this work, we have both a hardware design as well as a compiler that can do things automatically, completely transparently to the programmer. You can identify code. You don't have to do this part. This is auto-vectorization. You can actually, programmer can do the vectorization. Auto-vectorization, if it's possible to do by the compiler, you can do it. And then the compiler schedules and maps the data to the DRAM arrays, subarrays. And then it does the code generation using the bulk bitwise operations. So we have a full compiler pass. If people are interested, they can download it, use the MIM-DRAM code. Everything I said is open source, essentially, almost everything. OK, and we get significant performance energy and performance per watt improvements on workloads that are auto-vectorizable. So that's a disclaimer over here. Irregular workloads will not see these huge benefits. And you may see some huge numbers. These are actually real numbers. We verified them probably 100 times to make sure that these numbers are real. The reason you get these large numbers is in these workloads, you can actually take advantage of all of the subarrays in DRAM. So if you actually take advantage of all of the subarrays in DRAM, that's millions of bits at the same time. You don't add any logic, very little logic essentially. But compare that to a GPU. A GPU has a lot of things that don't do computation. Even though GPUs are much more computationally, let's say, efficient compared to CPU, they still have a lot of things that don't participate actively in computation, right? Whereas in DRAM, you can actually, every bit is working, let's say, assuming things are parallelizable. OK. OK, do we have time? 5 minutes. OK, I'll go through very quickly. So basically, you could say, oh, are you smoking pot or anything with all of these like processing using DRAM? And sometimes it's good to think about it. I mean, you do a lot of work on emerging memories. Sometimes it's not easy to make these real, right? So we wanted to test, can we actually do these in real DRAM chips? And we designed multiple FPGA-based infrastructures to enable this. This is one infrastructure. It's all open source. It's DDR3 based. And the idea is violating the DRAM timing parameters enables row clone. By violating activate-to-activate parameter, you can actually copy data between two subarrays. You need to know exactly which rows are mapped to which subarray, of course. But we are able to do that. Security people are able to do that. We can also generate true random numbers by reducing the latency of a DRAM access. Some cells, if you don't give enough time for the sense amplifiers to settle, some cells will be sensed correctly or incorrectly. And some cells, depending on how much you reduce latency, that cell becomes a random number generator. Because every time you access a cell, you're essentially sampling the sense amplifier noise, for example, or the bitline noise. So you can actually generate random numbers. And we've shown that in some other works. So in this work, we designed this FPGA board where you have an end-to-end system. You have an operating system plus application. And when the application does, for example, copying, operating system maps the thing to the destination, the source to the same page, same subarray. So a destination to the same subarray as the source. And then you ship the copying to a memory controller in the FPGA. And the memory controller executes that copying by violating the timing parameter, activate-to-activate timing parameter. And you do the copy, and when it's done, memory controller says you're done. And you can actually run real applications with this. assuming you do the copying reliably. In many cases you do. I'm going to show you results with that also. You could also generate true random numbers. So you can actually have a rand function calls. Rand function call gets executed in the memory controller over here by violating the timing parameter. It's not an easy system to work with or design, but it is doable, and we actually have some real results with it. If people are interested, we'd be happy to support it. And these are real results. This is the throughput of copying and initialization. And we get significant performance improvements, as you can see. The reason the improvements are huge, and I agree that they're huge, is because the FPGA has a very wimpy RISC-V processor. That's the one that's executing. It doesn't have a lot of latency tolerance mechanisms. Yes?
Does the DRAM offer TRNG bits natively, or do you need to inline post-process?
That's an excellent question. Yes, you need to inline post-process, unfortunately. We try to find ways of doing it without inline post-processing, but there's no way, actually. It's standard in a lot of random number generators. OK, so you can actually do more. That was copying and random number generation. More recently, in this work that appeared at HPCA, we showed that, again, commercial off-the-shelf DRAM chips, you can copy one row into up to 31 other rows with almost perfect success rates. You can perform the NOT operation with up to 32 operands, and you can perform 16 input AND, NAND, OR, and NOR operations. And the basic idea is, again, either consecutively or simultaneously activating multiple rows. So this is row clone. It activates one row in succession with the another row. But we figured out a way of actually doing activation. You activate one row, and then you then activate many rows. If you do that, you can copy the source row into the sense amplifiers, and then the data over here to many rows in the same subarray. That's the idea. Again, if you want to ask me how to do that, I'm going to defer you to later, because you need to actually figure out how you can activate multiple rows. And the reason you can activate multiple rows concurrently by violating the timing parameter is the decoder in the DRAM subarray is a hierarchical decoder. So some rows you can activate concurrently if you actually violate the timing parameter. And that hierarchy you need to know. You can reverse engineer a lot of these. In the paper, we have a lot of reverse engineering also. OK, so that was, let's talk about NOT operation. I've given you the NOT operation already, actually. If you activate the source row, the complement goes to the next subarray, the destination, or the other side of the sense amplifier. And there's another subarray over here, actually, that's connected in the open bit line architecture. And then you activate the destination row. Now you get the data value on the other subarray. It's in some other subarray, unfortunately, but you can do it. Now, you can generalize this. This is, I think, the fascinating part. Again, based on theory, if you have two rows over here and two rows over here, if you concurrently activate, imagine a primitive, you concurrently activate all four of them. What the sense amplifier would do is compare the average voltage of A and B to the average voltage of X and Y. Right? And if this is greater, this will become 1. If this is if that's not greater, this will become 1. Right? Now, by carefully adjusting values over here in the reference subarray, let's say this is VDD or VDD, you set it to VDD. And there's a way to set a cell to VDD over 2 in DRAM that was developed by Princeton folks. Essentially, this could be the reference subarray. Now, if you put X and Y over here, for this function, X and Y, function X and Y to evaluate to 1, X and Y should be both 1. Right? If any of these is 0, this function will evaluate to 0. And you know by now that it's an AND function, right? You get the AND in the compute subarray, NAND in the reference subarray. So essentially, if you're able to do this, you can do AND and NAND, as well as OR and NOR. You can generalize that too. OK, so that's the paper. With our testing infrastructure, with many DRAM chips, we tested a lot of things. And with multi-row copy, essentially, you get almost perfect copying. Clearly, almost perfect may not be desirable in scenarios, so we're looking at how to make it perfect. That's future work. And NAND, OR, and NOR is surprisingly high success rate. This is, for example, over here you get, with 16 operands, you get very high success rates, more than 90%. This was not expected for me, but still less perfect than copying as expected, because there's a lot of variation over here. Yes?
Quick question. So when you were doing this study, right, and you're recording this 99% success rate, are you looking this 99% success rate across multiple subarrays?
Yes.
Trying to do it across many subarrays. I mean,
yes.
If you are normally when we set right the latency of the DRAM, that's what is the word line down on time. That's what you're exploiting, right? With the same word line time, you want to transfer the same word line, so the sensor will write it back.
Yeah.
These are normally set based on the weakest possible bits.
That's right. Yes.
Right. So if we are targeting not the weakest bit, we will get the success. But as soon as they get to the weakest bit, not the sensor would not develop.
That's right. Yes.
So I mean, do you have a sense of are these experiments getting to the weakest part at a high temperature? Or
yeah. So we did a lot of studies. I didn't present all the results. We looked at data pattern, temperature, spatial variation, etc. We tried to get as much as possible, but we clearly cannot cover everything in the entire DRAM. We did it as much as possible, but there needs to be more work, for sure. But you have a very good point. It's about the weakest bit, but we also had looked at some experiments where we actually changed the latencies, because different subarrays actually may benefit from different latencies, different time amount of time you wait. And these are not the optimal result, either for the worst case or the best case, basically. So I think there's more need to be done to understand this.
And is it, do you know the vendor of this DRAM?
Okay, vendors are, yeah, of course we know the vendors. They're in the paper. SK Hynix. SK Hynix is the one where we could reverse engineer the best. Some other vendors are harder to reverse engineer. We'd be happy to work with them if they want to work with us. Yeah. But yes, it's a matter of also reverse engineering, because we need to understand because these are not published. I'm under, yeah. Yeah, but you can reverse engineer a lot. With the infrastructure that we have, you can reverse engineer a lot. That's a whole different area, which I'd be happy to talk about. Okay, but the takeaway is, I think, existing DRAM chips are already capable of a lot, as you can see. So if you can actually change things a little bit, maybe they can do even more. Right? Okay, I'm going to skip a lot. There's more. What else can we do using commodity memories? We have more results, which I'm not going to talk about. This was presented at IEDM last year. We had some new results over there, but I'm not going to talk about that. I will mention that you could, with lookup tables, you could do even more. In Flash, we have real Flash results with real Flash chips. And you can actually do more reliable computation, bitwise computation in real Flash, again, by exploiting the multiple row activation paradigm. This is actually very fascinating to me, because you can change the controller over here. In DRAM, we don't have a lot of, we can play with some timing parameters, but we don't have a lot of control. In Flash, you can change all of the voltage levels, for example, to make this reliable. And we made this reliable in this work. And we're actually looking at a lot of interesting things that could happen with bulk bitwise operations, and homomorphic encryption is one. You can operate on encrypted data using all of these bitwise operations. So these bitwise operations are very, very interesting, in my opinion. Maybe they're a bit undervalued. When we first wrote the Ambit paper, it got rejected 4 times, for example. The reason was, who uses bitwise operations? I'll leave it to the history to judge that later. Okay. Okay, so I think I took a lot of time. There's a lot more in our papers. One thing I will mention is critically important is adoption. Because you can design any hardware in the end, and it may be useless because nobody adopts it. And this is what we're working on, and I think a community is also working on as well. And a lot of the adoption issues are really, some of it is hardware issues, no question about, but a lot of them are applications, software. How do you ease programming? How do you make the interfaces easier to adopt? How do you design compiler support so that no one needs to write code for it as much as possible? System and security support. There are very hairy issues over here like virtual memory, which we are doing a lot of independent work on PIM, but I think this is one of the hardest issues in computer architecture today. How do you deal with virtual memory when you have huge data sets? Coherence, synchronization, etc. Runtime, I think runtimes are going to be important because as systems becomes heterogeneous, you need to have a data mapping and computation mapping problem. And people here are also working on it, multiple people. And infrastructure, that's why we build a lot of infrastructure to try to enable this thing. So PyDRAM, for example, took multiple years to build to do the computation, but it was important. Hopefully other people will use it also. So in the end, I think we need to revisit the entire stack because this is really a problem that's fascinating problem that spans algorithms to devices. But maybe we can get there step by step. Row clone is an example of step by step, for example. There may be some functions that are little. Even then, they still require changes across the stack. So they may not be easy to adopt. So it requires a persistent push, let's say. OK, so to conclude, I think if you want fundamentally energy efficient and high performance and sustainable architectures, I believe we need to solve the data movement problem. And this requires enabling computation close to and inside memory. I highlighted some major recent advances in processing in DRAM specifically. It can lead to orders of magnitude energy and performance improvements. And unmodified DRAM chips are already capable of computation. I believe memory should be designed as a combined computation and storage substrate, not as an inactive storage substrate as we do today. And for this, design mindset and flow and many, many other things should change. I think the future is still bright because there's a lot of research and design problems. And the good news is technology is on our side. The integration and packaging technologies are today getting to a place where we can actually integrate memory and logic in a much nicer way. And as I said, we have nowhere to escape. So we need to make this work, in my opinion. And it's good to also look at this picture. I don't want to be cheesy, but if you look at this picture, I think this picture doesn't separate computation, communication, and storage. We can, yeah. We have a lot of tutorials if people are interested in contributing. There's more coming up at ICS and ISCA. And a lot of things, almost everything I said is open source. We'd be happy to help. I'll acknowledge funding from many, many people. Without them, this wouldn't have happened. And most importantly, this is the most important part of the slide, I'll acknowledge my students. You can see some pictures and read about them if you're interested. With that, thanks for bearing with me. I'd be happy to take more questions.
Thank you, Onur, for an excellent talk. I think I'm going to just entertain one more question, if there's a question. All right, over there.
Yeah, thank you for this great talk. I'd like to specifically ask you about you talked about how we need to rewrite the algorithms, we need to rewrite the software. So from my understanding, your current work either needs like programmer expertise to say, okay, this whole thing I need to offload to PIM, or you can do some compiler tricks to identify that. So do you envision this going down to the CPU and doing this in a dynamic way where the compiler and the programmer has no knowledge and we can dynamically decide, okay, this is worth shipping to memory? Yeah. Or do you think this is too low of granularity and we need to stick at the compiler to application?
I see. So that's a very good question. I mean, in the end, all of them need to be explored. And we have actually explored a lot of these different things. We've explored doing this purely in hardware as well. Can we somehow identify things that we can ship to memory purely in hardware? It requires a lot of hardware complexity. It's possible to do, but the complexity is high, and the benefits that you gain are not very high. We've looked at pure compiler mechanisms, both in GPUs and CPUs. Memory-DRAM is one example, although it requires some changes to the hardware, as you've seen. Pure compiler mechanisms are also good, depends on how much parallelism they unleash, but depends also on what you can identify. So bulk bitwise operations, vector processing, if you can identify them well for workloads, you can get huge benefits. But for some other workloads, like irregular workloads, we've looked at a lot of irregular GPU workloads, for example. We had this work with NVIDIA some years back on transparent offloading and mapping. You get benefits, but not as much as what you would get if you actually went and redesigned your program to take advantage of near memory processing units. So in the end, it's important to explore all of these parts in the computing stack. In the end, if you ask me my opinion, I think there needs to be work done by the programmer a little bit to expose things, just like people do in machine learning, for example, today. And there needs to be a lot of work done by the compiler to optimize things. And there needs to be some support from the hardware. So in the best world, in my opinion, you need to modify the stack so that you can cater for a large chunk of applications. But smaller set of applications, if you're targeting, for example, copying, you can get away with relatively small changes.
Okay. Well, thank you, Onur.
Thank you.